right? Yeah. We haven't talked about binary tree for a long time. Yeah, binary tree a little bit.
We're going to look at the right side from top to bottom.
Yeah. Okay, so this is the binary tree. Yeah, binary tree. This is
1, 3.
By the way, binary tree. Yeah, 2. Binary means 2. One parent can have at most 2.
2.
Yeah,
One.
and then these nodes which doesn't have any kids, we call it leaves. And this one doesn't have parent, we call it
Root.
node. How many parents can a node have? How many parents?
1.
Yeah, at most 1. Yeah, this one doesn't have parent. It's called root. Okay, and this one. So if for a binary tree, if it if it has a 0 or 2 kids, we call it complete binary tree. Okay, complete binary tree.
Yay.
Okay, 2 nodes is complete. Okay, so let's see. This one is this complete. Is this complete?
Yeah, 1, 3, 6.
Is this complete binary tree?
No.
Why is that?
It has a hole in it.
Yeah, well done. Okay. And if we complete this whole, it's also a perfect binary tree because every level is every level is completed. It's called perfect binary tree. Okay. So if I stand from the left hand side, looking from the right, yeah, we talk about this on day 92. Yeah. So what can we see?
You can see 1, 2, and 4.
Okay, if we stand from the right hand side looking to the left, what can we
1, 3,
see?
and 6.
Okay, and then if I put it another one, 8, what can we see in both sides? Yeah?
8. And
So that will be 1, 2, 4, 8, and here will be 1, 3, 6, 8, right? Yeah?
No.
Easy, yeah? Is it?
Yeah.
Yeah. Okay, so we talk about breadth search, yeah? Breadth search travel level by level. What's the breadth search order for this binary tree?
1, 2, 3, 4, 5, 7, 6, 8.
Yeah, okay. How about the depth search? If we go for the left hand side, if we travel the left subtree first and then the root and then the right subtree, what we call it in order, right? This is in order. Left node, right in order. Oh, for the depth search, we can have different order. Yeah, we can have this node left right or left right node. Okay, so this is pre-order, this is in order, this is post order. One good way to remember this. Come on, one good way to remember this. We just check this n, which is the root. Yeah, where is it? It's in the middle. We call it in order. In the first one, we call it pre-order. In the middle, we call it in order. In the last, we call it post order. Right? So
I can't remember the pre and post.
look at this one. N is in the last,
Yeah.
so it's post. In the
But
first one,
I keep on thinking like the last one is pre.
okay. In this one, in the pre. Okay, so sometimes we also call reversed. We can do it reverse. For example, reverse in order will be R and L. Yeah.
I don't know.
Reverse. This is
I don't
pre-order.
know.
Reverse pre-order will be R.
And then.
NRL, and then reverse.
Yeah.
Reverse post order will be RLN, right? Yeah? Okay. So look, if we do this depth search recursion, yeah? Depth search, what do we get for the recursion? Pre-order. 1, 2, 4, 5, 3, 7, 8, 6. Yeah.
Yeah.
How about the post? How about the post order? How about the post order?
4, 5.
Okay, and what did we talk about? 1, 2, 3. This is called pre-order, sorry. Yeah, this is called pre-order. 1, 2, 3, 4. Okay, for post order, I think we are talking about this one, eh? So it's what? 4, 5, 2, 8, 7, 6, 3, 1. Yeah, exactly. Okay. So for the breadth search, we use the queue, right? So we put in the queue. For the depth search, we use the stack. Most of the cases, we use the recursion, which is faster to implement. Okay. So I'm going to implement the breadth search first. Define. Let's say it depends on left or right. Let's just say view. Okay, view of the tree. View of the tree. And then we have the root. And first of all, answer. Yeah, answer equals nothing. An empty list. Yeah, empty list. So if not root, we just return. Yeah, return answer. This is a special case we have to handle. Yeah. So now let's say put it in the Q. Q equals, how do we implement it? How do we use the Q? DQ.
DQ.
Double and
I
DQ.
definitely
Yeah.
said that first.
I said
Okay.
it first.
DQ. Okay.
Root.
So what do we need to put in
Root.
root? Yeah.
Root.
We put the root, we put the node in the queue, and when we dequeue it, yeah, dequeue means that take the element out of the queue, yeah, pop it from the other, pop it from front, yeah. First in, first out, yeah, first in, first out. So we need to put the kids in, right? Look, how can you go through this with me? Come on, can you go through this with me? How can we? This is the answer, yeah, answer. Come on, eh? Q equals root, yeah? I put a 1 here, yeah?
Yeah.
This is 1, so I take it out. So I take it out, eh? I take it out, I need to put it in the answer, yeah? Because this is the first time, right?
Yeah.
Okay. Now what happened? 1 has the kids 2 and 3. Yeah? So which 2, should I put the 2 or 3, depending on which side I'm standing at? Is from the left and right, yeah? Let's say I want to first, I want to get the left side view, yeah? So I need to put the 2 in, right? Come on, look at me.
Yeah.
I put the 2. Yeah? But I have to put it in a queue, 2 and 3 in here. And I take the 2 out. I take the 2 out, I put the kids 4 and 5. But 4, well, 4 is the left hand side view, so I put it here, right? And then 3, I take it out, I don't do anything. 4, I take it out, it doesn't have any kids. 5 doesn't have any kids, okay? Yeah. So, but if I want to do this right side view, the only difference is that the kids, instead of the first kid, I take the last kid, right? Yeah, am I right? This makes sense.
Yeah.
So while Q. So first of all, I need to take it out. Current. Actually no. Actually, what do I need to do? N equals the length of Q. This is the number of the kids. Number of the nodes in the next layer. Yeah, in the next level. And yeah. Okay, so now I answer the append Q0. If you want to retrieve the first node, or Q minus 1, which is the last node, yeah, and then for I
In range and
in range for range n, and if Qi, yeah, Qi dot left, if it has the left kid, and then we put the kid in, yeah, alright. Q dot append. Actually, we can do this x equals Q dot pop left, okay? Yeah, Q dot pop left, yeah? And then if x dot left, Q dot append x dot left. And if x dot right, Q dot append x dot right, alright? Yeah? Make sense? Okay, let me go through this again, okay? I think this is the little bit problem here. Yeah. Okay, so depending on from left or right, Q0 means from the left. Q minus 1 meaning we want to take the right side view, yeah? Right side view. This is just a very standard breakfast search. Now n equals length cube. N is the number of the what? Of the nodes in the next layer. Okay? So we can append Q dot. We can append either the leftmost or the rightmost kid with the to the view, yeah, to the answer. Then every time we can dequeue, we can take all the kids of the same level, top them out, and then push their kids back to the queue. Yeah. So another way of doing is this. Look, if we can do this inside, but here we have to check if I is 0 or if I is the n-1, right? Depending on what. So inside this we can check if the index is the first one or the last one. Yeah, this also works. Okay. Yeah. Make sense?
Yeah.
Okay, so breadth search. Okay, now let's go back to the depth search. So how do we use the depth search to solve this problem? Okay, I'm going to show you. Yeah, depth search is a little bit different. Okay, 1, 2, 3, 4, 5, 6. Okay, for the depth search. When we're traveling this, what information do we need what information do we need?
We need to know when is the last one.
Yeah, something like that.
The
Yes.
last travel.
Yes. Okay. So it depending. If we want to go to the left side view, yeah. So we do this pre-order. So every time we go to a new level. So obviously when we define this depth search, define DFS, we have this root, and we need to pass the level. And the beginning is 0, right? So when we pass down the tree, we go to the left, the level plus equals 1. We go to the right, the level plus equals 1, right? Yeah. But we need to store these in a dictionary, right? The first time, it depending on if we want to do this left side or right side view. If it's on the left side view, we want to update the key. It will be the level, yeah. Key will be level, and the value will be the node, right? So it depending if it's the left side view. The first time we visit a level, we remember it, but we don't. And then the subsequent visit, we don't update the value, right? And if we want to go to the right side view, we always update it with the pre-order, right? Or alternatively, we can swap the pre-order. Pre-order is this one, yeah. The 1, 2, 4. You see how I go? 1, 2, 4, right? So I do the depth search with 1, 2, 4. So this is exactly the left side view, right? But for the right side view, it's not, right? For the right side view, I need to do this 1, 3. On the other side, or I can do the 1, 2, 4, 3. When I visit it, yeah, look 1, 2, 4, 1, 2, 4, and then what? 5, 6, 3. Yeah. If I want to use this sequence to do the right side view, which is 1, 3, 5, 6. You see? 1, 3, 5, 6. You see? Yeah. So how do we do that? We use a dictionary. Yeah, we use a dictionary. So if not root, obviously we just return. We don't do anything. Yeah, depending on what do we do. Root or left. Yeah, root or left. Level plus 1. Right, and then now I visit this tree, so I can do what? I can here. This is the code. If I have this data here, data is a dictionary. Default dictionary. Yeah. Default dictionary, which is the integer. The value default type will be integer, the level. So then I can do this data level, yeah, level equals root dot value, and then I can travel the right tree level plus 1, right? When we go down the tree in the next level, we have to update the level, right? Because look, this is level 0, level 1, level 2. When I travel the left tree, plus 1. When I travel the right tree, I plus 1. Yeah. So once I do this DFS root, I give a beginning level which is 0. Then here. Okay, then you tell me if I do this, the data level will be the left side view or right side view? Choose one.
Right.
Yeah, why is that? Right is the
Right.
answer. Why? Why is that?
Because that's what we're looking for.
Good answer. That's what we're looking for. Because look, we keep updating. We keep updating. 1, 2, 3. Okay, so let's take this example. 1, 2, 3. What happened? What's the sequence? 1, 2, 3. Right? Okay, so the order of visitor node is 1, 2, 3. So the order of look, there are 2 nodes at level 1, right? So data level 1 equals 2. And then data level 1 equals 3. So what's the data number 1? What's the data number 1 here at this point? We are updating. When we traversing using depth search, we are updating the dictionary. The level, the key is the level. Okay? So listen to me here. Data 1, 2, 3. So what's the data 1? What's the final value of data 1?
3.
Yes, 3. Because look, we first of all, data 1 equals 2, but we visit the tree in the pre-order, so it means the 3 gets visited last. So what does it mean? It means the last node visited will be updated, will be used as the right side view, right? Yeah? Yeah? If we want to do this opposite, so we need to swap these two, right? We visit the right tree first, and then we visit the left tree. Or alternatively, we can check this. If the first time we update it, so if level in data, then we do this. If level not in data, yeah. If we does the first time we visit a new level, we record it, then it will be 2. The 3 will never get the chance to update. Right? Make sense? Yeah? So once we get this, the answer, we just need to push the answer to it. So for I in sorted, we need to sort it the data.keys. Yeah? The data.keys will be the levels. The levels in sorted answer will be 0, 1, and then we answer the append data I. Okay? Then that will be the answer for the depth search for the levels, left side view or right side view, depending on how do we visit the binary tree. Alright, Ryan, or you lost a little bit?
Not too much.
Not too much. Do you understand what I'm talking about here? Yeah? It depending on, look, if we want to look here, this simple tree. From the left, if we want to get the left side view, yeah? If we want to get the left side view, let's talk about this pre-order, yeah? Node left to right, okay? Node the left to right will be 1, 2, 3, okay? 1, 2, 3. 1, 2, 3, okay? 1, 2, 3. The depth search. We visit the depth search, but for when we visit the node, we pass the level. Yeah? We pass the level. So we use the level as the key to store the values for each level in a dictionary, in a hash map. So if we visit all the tree in 1, 2, 3, right? Yeah. If we visit the tree in 1, 2, 3 and we update the hash map, first layer, second layer, the data 1 will be 3. That's the right side view, right? Or if we want to update the hash map the first time, we don't update it the second time. So data 1 will be 2, then that's the left side view. Alternatively, we can do this node right R will be reverse in order. If we do this in reverse in order, it will be 1, 3, 2, yeah? So there will be 1, 3, 2. So if we update this, then that will be the opposite. It will be opposite, right? Yeah? Yeah?
Yeah.
So that's the depth search. And the previous one is the breadth search. 1, 2, 3 is easier. For the breadth search, every time we just take everything out because the nodes in the queue belongs to the same level. So once we know the nodes on the same level, we can append the leftmost, which is located at Q0, yeah? Or we append the last node, which is Q-1, Yeah, depending on if you are looking from the left or from the right. Okay. Yeah, that will be for today. Bye bye. Yeah, the time complexity is also ON. Yeah, if the n is the number of nodes in the binary tree. Okay, and we're using additional space, which is the queue or stack. Okay, bye bye.
Bye.